All right, so to find this derivative, I know it's been a little while, but let's check in, see how well you remember. Remember, we have to do it implicitly. And so we're going to do the derivative of x squared, which of course is 2x. Then we're going to do the derivative of y squared, which is 2y, y prime. That's the part that you got to remember when doing those implicit derivatives, right? Equals the derivative of 49, which is? 0. Oftentimes, if you find yourself making a mistake on one of these types of problems, oftentimes that's actually the culprit right there, is we forget to actually take the derivative of just the constant term. All right, we're not done though, because I do want to actually solve this to be y prime. So let's go ahead and solve that through. That means I'm going to be moving that 2x to the other side, so I'm going to subtract that from both sides. And then I'm going to divide both sides by the 2y. And so I end up with negative 2x over 2y. And then having gotten to that part, I now can say that y prime simplifies down to be a negative x over y. But we're not done with this problem, right? Because in this one, we're specifically finding the derivative, yes, but at x equals 1. And so we now need to be able to figure out what is that derivative at x equals 1. You got a couple different options on how you can get there. One is that you can now go and figure out what is the y value when x is 1. Or we could rewrite this equation right here for our derivative in terms only of x. Now, I have a feeling most of you will have just plugged 1 in here for x and then solved for y. That's a good and valid method, but I feel like I need to shake things up a little bit, so I'm going to show how we can do it by writing the equation all in terms of x. So, I'm going to try to replace y with an expression only in terms of x. In order to do that, that means I'm going to go up to my original here, and I'm going to solve that equation for y, and then plug that in. So when we go to solve that original equation for y, I'm going to subtract the x squared from both sides, so I'd end up with y squared equals 49 minus x squared. And then we can go ahead and take the square root of both sides to get rid of the squared on the y. And so then that gives us the square root of 49 minus x squared, kind of. There's something slightly off about this last line that I just wrote. What's missing? Yep, the plus or minus. Remember that when we take the square root of both sides of an equation, we need to account for both the positive and the negative square roots. So we put that plus or minus out in front of it. All right, which means that now I can go back and plug that down in here in order to be able to continue working on my problem. So then, let's go ahead and scoot this up just a little bit here. We can then say that y prime equals a negative x over plus or minus the square root of 49 minus x squared. We just want to know that we can do that. And yes, you're probably noticing we got a negative here, we got a plus or minus here. Basically, those will end up canceling each other out. We could actually write the whole thing, instead of a negative here, we could just put the plus or minus there, and it would have the same effect. If you want to, you can. If you're wondering what the heck I'm talking about, you don't need to worry about it. All right, now we were still trying to figure out, remember, what is the derivative at x equals 1? So, I'm not done quite yet. I still now am going to take that x equals 1 and plug it into this equation. So we're going to go y prime equals the negative 1 over plus or minus root 49 minus 1 squared. And figure that out. So then y prime is going to be plus or minus 1 over root 48. Which we could get into all sorts of things about how we could simplify that radical. We could rationalize the denominator, all sorts of stuff like that. Or we could actually just get it as a decimal. And I'm kind of in a decimal mood today. We didn't specify on this one, so we just need to pick one. Let's go ahead and just turn this into a decimal then and get that value. So then this is going to equal about, because we are going to have to do a little bit of rounding here, plus or minus. All right, and so there's our calculated value. And I knew that my answer here needed to be somewhat close to 0. I knew that it couldn't be a really big number or anything like that, partly because I'm looking at the number that I'm doing here, and I know I'm going to be doing 1 divided by a bigger number. You know, root 48 should be close to root 49, which is 7, so it's going to be close to 1/7, that sort of thing. But I can also think about what's happening visually on this one, because you've actually made the graph of this equation before. Now, this was back on that that worksheet where you had to fill in all of those implicit graphs and see what they look like. So you did this one. And so what we just found, remember how our answer had that plus or minus in it? What we just found was the slope at this point and at this point. And you can see here why we needed to have the plus or minus in there, because at one of them, that slope is decreasing, and at the other one, that slope is increasing. All right, so having done that, I'm now going to bring you back to that work we did yesterday. Remember yesterday we played a little bit with derivatives, trying to figure out how many different ways you could come up with a derivative. I want to do that same kind of an idea. So here's a new function, and I want you to be able to try to think how many different ways can you find the derivative of this particular equation. Remember, I want you to be creative and come up with as many as you can. All right, now, as I've been walking around looking at people's work, there's certain themes that jump out. Almost everybody, especially because of the problems that we started with class, start by going in two main directions. The first direction is that we can just go straight up with implicit differentiation, where we find the derivative of the left side, find the derivative of the right side, and just are done there. That's not the only one that would involve implicit differentiation, but that's all there is to that particular method, is you just start by doing the derivative implicitly. The other very popular method that I've seen is first solving for y, and then finding the derivative, where we can just do dx over dy at that point. Okay, one little note on that one though, if you did do that and solved it for y, you'd end up getting y equals a square root of that, right? Remember that that square root should be plus or minus because you're taking the square root of both sides. I saw a couple people who did that who just left that part off. I want to remind you of that part. But there are more methods. There's definitely more methods. So I've started to see a few more creative options coming up here. Like I've seen some of you where you've thought, well, maybe I can just move this y squared over to this side. And so I've seen some of you where you've divided both sides by y squared, in which case you're actually doing, I'll just write it this way. When you divide the y squared by y squared, that gives you 1 equals. So then you're doing 4x squared plus 12x plus 9 all over y squared. And then we're finding the derivative of that. Some of you have taken that same idea and you've actually varied it just a little bit, and you've turned it into 4x squared plus 12x plus 9 times y to the negative 2, and then you're using product rule. A few more ideas, starting to think outside the box, right?
Yeah.
And there are more.
There's more.
Of course, there's tons and tons and tons of ways, but one way that I particularly want to focus your attention right now, because a couple people have discovered this, and I want to see if everyone can notice this one too. There's another way that you can write this.
No way.
See if you can figure out what that is and how that would apply here. So a number of you did now find out what else we could do there, because this quadratic over here, yes, it is factorable. So another option is that we could take our y squared and set it equal to the factored form, which is 2x plus 3 squared. Okay, so we could find the derivative of that implicitly now. And if we found the derivative of this implicitly, over here we'd be using chain rule. Okay. Alternatively, I don't know if anybody came up with this, but I'm going to throw it out there. You could also then write this, therefore, as y squared equals 2x plus 3 times 2x plus 3, and then it becomes a product rule, if you find that derivative implicitly. So another way that we can manipulate it, come up with a different method. But looking at this equation here, if y squared equals 2x plus 3 squared, what does y equal? 2x plus 3, basically. Technically, it'd be plus or minus 2x plus 3. But then, I could then find the derivative of that, right? What would the derivative of that function be?
Plus or minus 2.
Yep, just plus or minus 2, right? Another method that I heard a person say is you could do guess and check. I mean, it wouldn't necessarily be fun, but I mean, there's ways to do it, right? In fact, there's lots of different ways that you could go about doing this. Like between yesterday's problem and today's problem, nobody came up with possibilities of graphing it. If you could graph the implicit function, then you could try to figure out what its slope is at a given point, right? You could even revert back to limits. You could do like difference quotient on it and find out what the limit is as h approaches 0 and little things like that. All of these are valid techniques, right? Not necessarily always the ones that we want to do, but they're techniques that we can do combining with some of these. And of course, yesterday, remember, we also at the end started talking about all the other resources we could use. Like if you're totally stuck on a problem, you can ask a friend, you can ask an expert, you can ask the internet because Google knows everything. Not really, but it could at least help if you're feeling stuck or something like that. So there are lots of different ways you could go about, lots of different resources. And so what I'm hoping that you're starting to see out of this is that while our minds automatically tend to just go to the same ones, because they tend to be the ones that we use most often, remember that those aren't the only ways to do these types of problems. And this activity isn't just about how good are you at derivatives. It's a nice practice for that, but I could give you a similar problem that has nothing to do with derivatives and it would still stretch your thinking quite a bit, just in terms of how do we break out of the box and actually start thinking about these math problems a little bit more creatively. Because being able to think about them creatively is actually a huge step that oftentimes we ignore in math class, but actually is a big deal. All right, that being said, well, we got to go into a little bit more procedural work and take a look at some derivative practice based on where we're going today and where we've been recently. So, please just go ahead and find the derivative of this function. And as we go today, if you ever get stuck on a problem, remember some of that creativity that we've been talking about. It might help you get unstuck as we go. All right, so as you're taking a look at this problem, one of the first things that's probably jumping out to you as you look at it is the fact that we have this natural log of 2 here. What is the derivative of natural log of 2? The natural log of 2 is just a number, right? It's just a constant. So the derivative of natural log of 2 is 0.
Wow.
Remember, natural log of 2 is a constant. This is no different than if it was 2 to the power of x over 3 or something like that. And so now that we know that, now we can go ahead and find our derivative. And you got a couple different options about how you might go through it. Again, you can think about it creatively. There's lots of different techniques you could use. Some of you will actually just use the quotient rule here. And that's fine. You can use quotient rule. You'll end up with a few derivatives that are 0, so one of your terms on the top will totally disappear. And it'll all be over the natural log of 2 squared. And then you could simplify from there. But I think that's probably the longer route. For me at least, I'd rather not have to do the whole quotient rule when I don't have to. So for me, at least, and again, there's lots of different ways you can do it. This is not the only way. But for me, I actually started by rewriting this as 1 over the natural log of 2 times 2 to the x. Because this whole thing here, that's just my constant. It's being represented in this function. And of course, when I go and find a derivative, the constant is just going to stay there exactly as it was. And so I can just do 1 over the natural log of 2 times the derivative of 2 to the x. So now we just have to remember what's the derivative of 2 to the x. Well, e to the x, of course, the derivative was e to the x. So that hopefully helps you remember that 2 to the x is where we start, but it's not where we finish. What do I need to multiply the 2 to the x by here? Yep, the natural log of 2. And so, this is my derivative of the 2 to the power of x. Notice my constant was just hanging out front as I went through. But now having done that, I hope that you can see how you can then simplify your answer a little bit. And whichever way you did this, even if you did it with quotient rule, you're still going to end up with the same simplified answer of just 2 to the power of x. Now, if you did it with quotient rule, this is what you would have ended up with. Now, notice on the top here, I have the natural log of 2 and the natural log of 2 multiplied into the top. So I got 2 natural log of 2's on the top, and notice I have 2 natural log of 2's on the bottom, and so all of those would cancel out, and again leaving me with the 2 to the power of x. Now practicing what we just picked up on yesterday. All right, so when we do this one, the basic derivative of inverse sine is this. Now, in this case, though, it's not inverse sine of x, it's inverse sine of x squared. And so that means we're going to be using chain rule. So instead of it just being x squared here on the bottom, we're going to make that into an x squared squared. And then I have to multiply by the derivative of the x squared, which of course is going to be 2x. And we could clean this up a little bit from there. Not a ton, though, as it turns out. So I'm going to end up with 2x over the square root of 1 minus x to the 4th. And we can just call it done right there. All right, continuing our theme, please find the derivative of this one. All right, now if I was just going to be doing the derivative of inverse cotangent of x, this is my derivative of inverse cotangent. But it's not just of x, it's of 3 to the x. So instead of it just being an x there, we're actually going to be doing 3 to the power of x squared. But then that also means that I have to multiply it by the derivative of 3 to the x, which is 3 to the x natural log 3. All right, and now we're just at the cleanup phase here. So then, y prime is going to equal a negative. Let's go ahead and put that 3 to the x natural log 3 on the top. And on the bottom, we have 1 plus 3 to the power of what? Yep, it's a power to a power, which means multiply the exponents. So I'm going to do the x times 2. So that's going to be 3 to the power of 2x. And I don't see any way that we could cancel out the 3x's on the top and bottom because there's not a 3x in that term. There's nothing else I can do really to clean it up, so this would be our final answer. Continuing with finding our inverse trig derivatives. Now one that maybe is a little bit more involved. Right, now I think most people when they do this one, we just start taking the derivative implicitly. So that's the way I'm going to be showing it here. And the derivative of inverse sine is 1 over the square root of 1 minus x squared. But of course in this case it's not going to be an x squared, right? What's inside is a y. So it's going to be 1 minus y squared, but then I have to multiply by the derivative of y because this is chain rule. And so then it's going to be times y prime. If you chose to write that y prime on the top instead of the 1, so you wrote as y prime over the square root, that's great. All right, and then equals. And now we have to do the derivative on the right-hand side. And what rule do we need to use to find this particular derivative? Yep, product rule. Now, different people look at it different ways. Some people just pull the 8 out, and then they do x times y. Personally, when I do it, I just make it into an 8x times a y, and that's how I think about it. Both are valid, both work. All right, but that's the way I'm going to show it. So I'm going to do original 8x times the derivative of y, which is y prime, plus the derivative times the original. Derivative of 8x is just 8, and then times the original y. All right, so now that we are here, we now need to be solving it for y prime. Remember, to solve it for y prime, move all the y prime terms to one side and all the non-y prime terms to the other side. So in this case, I would subtract the 8xy prime from both sides. And then you can worry about factoring that out from there. so then when we move it all together and get it to be y prime, this is the sort of thing that you'd be looking at. Now, could you have solved it other ways? Yes. Like right now I see this fraction within the fraction and I really want to clean that up, but I don't want to really go off on that rabbit trail right now because my concern was getting the y prime by itself. But technically this would not be considered a totally cleaned up answer. Let's just acknowledge that. And so because of that though, some of you might have actually decided, well, I'm going to start way up here by multiplying both sides by that square root so that I won't have that in the denominator. That's a great way to approach it at that point. There's lots of different orders you could have done it in to create equivalent solutions. Now, one other thing I want to take a look at here is I started this the way that I expected most of you will have started it. However, was that the only way I could have started it? Well, if you were looking at this problem at the very start and you did not remember what the derivative of inverse sine was, you could have just changed the form, right? If you wanted to, you could have turned this into y equals sine of 8xy. And then we could go from there as well, right? All right, next up, I'd like you to please find the derivative of y in this case. Back to our exponentials a little bit here. All right, so I imagine that most of us will have started by just going ahead and finding the derivative implicitly here. So let's go down that road. So that's going to be the derivative of 2 to the power of y. So this, yes, is going to be using chain rule. So that's going to be 2 to the y times natural log of 2. But then remember, it was 2 to the y, not 2 to the x. So that's going to be times y prime. And then that is then going to be equal to the derivative of x, which is 1. And, of course, I need to still find the derivative of y, so I want to have this thing solved for the y prime. So I'm going to go ahead and divide both sides by the 2 to the y natural log of 2. And we then can find that y prime here equals 1 over 2 to the y natural log 2. And we found our derivative of y. We got y prime. Now, I said that's the way that I expect that most of you will have started it. And yes, this works well. This gets us our final answer. But remember in that last one, at the end, I talked about how you could have rewritten the equation in a different way. Can we rewrite this equation in a different way? Yeah, we could write it as a logarithm, right? And so if I write this as a logarithm, it'd be log base 2 of x equals y. Well, these two are equivalent equations, right? They're both saying the exact same thing. They're just written in different ways. So does that mean that I just figured out what the derivative of a logarithm would be?
Yeah.
Kind of, yeah. In fact, that's where we're headed with this. We want to find the derivative of a log function so we can know what the derivative of it is going to be and actually add it to our derivative rules. And so, like if I'm going to find this derivative, the very first thing I would do is, because I don't know the rule yet, is write it as an exponential. Because then I can find the derivative of that exponential, which is what we just did. So we already know this much of this problem. We already know that y prime equals 1 over 2 to the y ln 2. But like with all of our previous derivative rules that we found, I want to end up with an equation for y prime that equals something in terms of x, not in terms of y. Take a look at what we have up here. The answer is up here someplace. How can I rewrite this expression to involve x instead of y? Notice up here, we are told that 2 to the y equals x, which means that this 2 to the y down here also equals x. And so I can replace the 2 to the y with the x, and I now have my derivative of a logarithm only in terms of x. So, as it turns out, if I'm going to do the derivative of log base 2 of x, that's going to equal 1 over x ln 2. Based on that, if I gave you y equals log base 7 of x, what would y prime equal? What do you think? Well, the only place the 2 showed up was inside the natural logarithm. So, yeah, that's where the 7 would be. Okay, well then, what if I just gave you y equals log x? Yeah, good. I'm hearing lots of people say ln 10. Because yes, it's going to be the natural log of 10 in that case. Because remember, log just means log base 10. That sounds like a good thing to be able to put in as a rule, right? So on your derivative rules page, we can add how do we find the derivative of a logarithm. Now, once we have that down, there is one other logarithm that we have not discussed here, right? What would the derivative of natural log of x be then? All right, so if I'm going to do that, of course, natural log is the same as log base e, right? So we're going to be doing it for log base e of x. So then, that would give me 1 over x natural log of e. But that, of course, can simplify, right? What does the natural log of e equal? 1. And so then, the whole thing then would just equal 1 over x. So once again, e and natural log ends up giving us a simpler version of our derivative. And of course, add this also into your derivative rules page. So having gotten those rules down, we now can go ahead and find these derivatives, whereas we couldn't have before that. Please do so on your own first. All right, so for doing this derivative, we of course need to be using chain rule, right? So we're going to do y prime equals, the derivative of natural log is 1 over x, so it's going to be 1 over whatever was inside, so that's going to be 1 over sine of x, times the derivative of sine of x, which of course is cosine. Well, we can simplify that. So yes, I would like you to. What does that simplify down to be?
Cosine over sine.
It's cosine over sine, which is?
Cotangent.
Yep. So the whole thing just equals cotangent of x. All right, another one to practice with, please. Please find the derivative of this function. All right, so then for this derivative, we're going to go y prime equals 1 over, instead of x, it's e to the x, but then it's got to be times the natural log of 7. But again, remember I'm using chain rule, and this e to the x is my inner function, so I have to multiply it then by the derivative of e to the x, which is, of course, itself, e to the x. Notice this does simplify once again, because this e to the x is going to cancel out with this e to the x, and the whole thing is just going to equal 1 over the natural log of 7. And yes, this is a number, and just as a slight rabbit trail to go down and talk about, it actually could make sense that this would be a constant, because I could actually rewrite this logarithm in a different form. I could have also done this one by going y equals x times log base 7 of e. Because remember, we can take an exponent out as multiplication. And so notice, that ends up being x times a constant. And so it would make sense then that it would just be a constant as an answer. Now, why that then gives us this? That actually comes back to the change of base formula. Because if I were going to then calculate this, actually I want to kind of go down this road. I want to finish this out. So y prime here equals log base 7 of e. if I wanted to actually calculate that value, I would then have to do the natural log of e over the natural log of 7. That's change of base formula. And that's why it would equal 1 over natural log of 7. So, yes, it could also have been done another way. All right, next up, I think we kind of got the rhythm down. Now let's go and find this derivative now. All right, so when we use a chain rule here, we end up with this equation. Then we could look to clean it up a little bit here. So we got y prime equals the 6x plus 2 all over natural log of 2 times the 3x squared plus 2x. Is there any way that I can further simplify this? Yeah, it's not sounding like we're finding anything that could be simplified. I mean, you might be seeing that we could factor the x out of that binomial there, but you'll notice that wouldn't let us simplify the fraction anymore past that because I don't have an x in every term in the top. And the natural log of 2, I'm not going to be able to divide that out of everything. Yes, I can divide both of these by 2, but I can't divide everything on the bottom by 2. So yes, this is as good as it's going to get. We call it done there. All right, last problem that we're going to do together now. So we're now going to write the equation of the tangent line to the curve. Of course, the first thing you need to do is find the derivative then. Since we're doing tangent line, that means we've got to find the slope of the tangent line with the derivative. Which rule are you going to use to find the derivative here?
Product.
Yep, product rule. So make sure you are in fact using product rule here. All right, so I found my derivative and I cleaned it up a little bit here. Now I can go ahead and proceed. So if I'm going to write the equation of the tangent line, the first thing I need is the slope of the tangent line, which means that I'm going to take my x value and I'm going to be plugging it in for x in my derivative function here. And at this point I went ahead and changed the name to m just to kind of show that now I'm actually finding the specific slope of it. So I got 1 plus 2 times 1 times the natural log of 1. What is the natural log of 1?
0.
0. Because it's basically saying e to the power of what equals 1, and anything to the power of 0 equals 1. So then that's really 1 plus 0. So then we can find that our slope is just equal to 1. You now have your slope. Please finish finding your equation now. And so we plug in our slope and our point into the old y equals mx plus b, or yes, you can use point slope form. I think it's actually a very powerful way to do it. I actually prefer point slope form for this, but when I do that, I find that people give me really curious looks and wonder what the heck I'm doing because they aren't as comfortable with it, but it's a great way to do it, so don't lose that. All right, and so now that I found my y-intercept and my slope, I can go ahead and finish writing my equation. So my final equation here would just be y equals x minus 1.